I can find. Do. So I was thinking maybe perhaps some manifold theory or something. So I think everybody here knows what a manifold is, right? Is that right? I mean, setting aside topological nuances, you know what a manifold is, right? I say no. I mean, you have a sense of what it is. It's a very curvy sheet. So I think it might be fun in here to tell you guys about what's a fiber bundle, and to try to describe the connection of fiber bundles and what's called gauge theory in physics. So I think I'd like to try to do that with you guys, because I'm starting to kind of run out of. It's starting to get a little bit too far into this for this. And so probably what I'll do is to invent a homework monstrosity to complete this thought for you guys. Something like that, all right? Something like that. But let me just give you. Let me give you just the big picture ahead of what I want to describe for you with gauge field theory. The basic idea of gauge field theory is that you've got some kind of manifold, which is, you think about it as being space-time, right? And then on this manifold, you have functions that we identify as fields from physics. So those functions have the manifold as their domain, right? And so maybe you've got something like, I don't know, phi, and it takes its values up in, I don't know, whatever, some vector space, which describes some kind of physics. It could be an SU2 matrix or something else, or it could be a complex number. We talk about a wave function, perhaps, I don't know. Anyway, there's some kind of physical symmetry, and so attached to that function is some notion of some sort of symmetry group. And so quantum mechanics first studied wave functions which, have some sort of global symmetry. So, for example, you have something like phi star phi. The Lagrangian would be something like, there's some scale factor, I don't know, some kind of mass or some kind of number out here, I don't care what it is. Anyway, so like a wave function conjugate times a wave function. And the thing is, if you take phi and you transform it to e to the ig phi, this would be a global symmetry. I say global because there's no x dependence to the g. And you can easily see that if you did that, and you have that complex conjugation, right? So like, if that's the transformation for the field, then the conjugate transforms by e to the minus ig. Everything's commuting here. So the e to the ig and e to the minus ig, they cancel out, and the Lagrangian's invariant with respect to that phase transformation, right? So then the question but there's something sort of at odds with special relativity about this idea, that because, again, this phi is some kind of function of x. Well, that x is really space and time, okay? But this is at odds with special relativity because, how can you do a transformation which is the same everywhere at space and time? Doesn't that sort of violate the basic idea of special relativity that things are local? So from this, physicists say, well, this isn't quite the right idea. Maybe that g shouldn't just be a global constant. This g actually itself should be a function of x, a function of the coordinate on space-time, right? That's a local symmetry transformation. So in some sense, you can think about there being copies of your symmetry group attached at each point in the space-time. And a local symmetry transformation says you're doing a different rotation in each copy of the group at each different point. But if it's a local symmetry transformation, it stands to reason that these different transformations should be sort of glued together in some sort of nice enough way, right? I mean, like, if I've got two really, really close together and I'm rotating by that much there, maybe I should be rotating by just that much there or something like that. You know, there's some sort of notion of continuity of these transformations. So then the question is, if you consider such a thing, what does that mean? This notion of local gauge symmetry. So you study how that forces that it actually, when you study it carefully, it will force you to modify the Lagrangian in ways which you might find surprising. It makes you replace derivatives with what are called covariant derivatives, and ultimately it leads to you introducing a new pure gauge term to the Lagrangian. When we study these things more carefully, the mathematics of this, that covariant derivative has to do with what's called a connection on a principal fiber bundle, and the way the local gauge symmetry transforms gets connected to what's called the connection form on the principal fiber bundle.
So what is a gauge though? There's a gauge symmetry, but what is the exact definition of a gauge again?
A gauge symmetry is, like I said, a local symmetry.
Oh, so the gauge, like when we talk about gauge, we're talking about the gauge symmetry.
Yeah, I mean, gauge symmetry, it goes back to, I'm not absolutely sure, but I think one possible reason for the term is just what we see in physics, that there's a gauge symmetry, for example. You know, I say potential energy is mgy, right? You're like, no, it's not. Potential energy is mg times y minus y naught, right? That's a gauge symmetry. The zero for the potential energy is not physical. There's a translational invariance to the physical equations. That's gauge symmetry. In electrostatics, it's much more interesting, because in electrostatics, you learn that the electric field is the gradient of a potential function, right? Well, minus the gradient of a potential energy function. Well, the potential energy per unit charge, well, that's equal to minus the gradient of phi plus the gradient of some other thing. Oh, I'm sorry, that's not right. The curl of, no, still not it. Curses. Yeah. Anyway, I can add something. I'm sorry, I can add a constant, right? I guess it's still a constant. What's more interesting, though, is the magnetic field is the curl of a vector potential, right? And that's the same as the curl of the vector potential plus the gradient of anything. For example, Pac-Man. So the vector potential that you learn about in your fields and waves course, I hope. Please tell me you learned about the vector potential in your fields and waves course here. You're an electrical engineer, aren't you?
Electrical.
Are you electrical?
Yeah, it's been a while. But
You had a field and waves course. You did talk about the vector. You talk about the vector potential there.
yeah. Well, I think not explicitly. I feel like we touched on it, and then like it's kind of just like
Insignificant. Insignificant. You hurt me with that. So what's the formula for potential, like voltage? You do what? Integral from the origin, whatever that is, to R of the electric field, right? Well, let's get more specifically. K, the density of R prime over the distance between R prime and R, d3 R prime. That's the formula. That's the formula for voltage in terms of the integral of the. This is the integral. Oh, I'm still wrong. There we go. That's better. So the integration over volume of the charge density. What this does is it finds the Coulomb field. And squared. Sorry, the Coulomb field. Oh, it's still wrong. Dang it. Potential. Just that. So this gives us the voltage for a charge distribution by adding up the voltage of each little bit. What this is k dq over script r, the distance between charge in here. The A I'm talking about is actually the integral over volume, I think, if I remember right, of, how's it go? Dang it. Oh man, I am rusty. There's a similar integral you do over current density to get the vector potential. But anyway, the curl of that's the magnetic field. The larger point is that you can shift the voltage by a constant, you can shift the magnetic field by a gradient. If you put those both together, you get a one form. And that one form you can shift by the exterior derivative of a function. That speaks to the actual gauge symmetry of electromagnetism. And it is Weil who learned in about 1920 that you could view electromagnetism as a U1 gauge theory. Attaching a copy of the circle to each point in space-time and viewing it as a gauge theory produces the equations of electromagnetism. Actually, that's not true. In 1920, he proposed the idea to Einstein. Einstein said it's crazy. And then, while respecting Einstein, of course, was like, oh, stink, or whatever. But then, he wouldn't give up on the idea. In 1929, he wrote the paper which corrected his physical. He had a wrong idea physically about what he was doing. He corrected that idea, and that gave us the first example of what we now understand as gauge theory. Then in the 50s, in like 1957, somewhere in there, Yang and Mills did it for SU2, for a gauge group of SU2. They did Weil's idea for a non-commutative gauge group, and that led to what we now know as SU2 gauge theory, which ultimately laid the groundwork for like the electroweak theory and other things. In 57, or somewhere in there, Udiyama, the Japanese, did it for an arbitrary gauge group. So, but at first, these ideas were just games theoretical physicists were playing, completely without any information about that. And in parallel, in the mathematics community, people were studying fiber bundles because of questions in topology, the Steenrod, Eilenberg-Steenrod axioms. But this ultimately led to the study of connections and fiber bundles. And in about 1970 or so, all of a sudden, the physics and math community realized that they were studying the same thing, but from radically different interpretations. In fact, my advisor was one of the first people to understand this in the early 70s. He said he had a few grad students from Princeton that were visiting for a talk or something, and he just said, oh yeah, the connection form on the fiber bundle is the gauge potential in physics. And they're like, what? So, he's happy. For a time, he was ahead of them. But then physics has kind of gone a long way past that now. But anyway, I'd like to try to explain a lot of the details of that to you over the next few classes. I think we should do something besides just my pet project, if you don't mind. Yeah. So I will start abusing. That's right. I do need to do that thing you just said as well. That is true. But oh, I'm sorry. We're over time. Let's not anger the janitor. Sleep. We gotta go.